like Petrified Forest National Park with all those logs.
As you said, the higher the water, the quicker it moved. While as it was dissipating, you'd have a lot of logs floating.
Right.
Would help account for a lot of the erosion, especially as the final stages of.
Oh, yeah, if it got shallow. Well, the logs that float at the top,
Right.
your main erosion would be down lower. And a lot of times you'd be carrying huge chunks of rock. In fact, some of these chunks are probably the size of this building to start off with, and they get whittled down. But as they're moving, they're eroding. They're the erosion tools for the water carrying on the bottom. Only when the water drained enough would the logs do that, but they would jam up pretty quick.
So what happened to the trees in the initial hit, the contact? Where did they play in the whole process?
I don't think they play much of a process.
It's jumbled throughout the whole thing, and then as it's...
Yeah, they mostly float on the surface. I believe after the flood they were floating in the pre-flood ocean for a while, and you might have had whole ecosystems moving around on the ocean for a while. Kurt Wise talks about this, and that's I think he's got a good model on the floating log mats after the flood, and that could cause some of the animal dispersions. Yes.
A lot of the evolutionists call this river rock.
That's right, rounded river rock.
They think it's because of a slow-moving river instead of a large sheet thing. And
Yep.
also, we have some cuts in the hogback and other things that just cut right straight through.
Yeah, you have some water gaps in this area, and planation surfaces and pediments. In fact, when they're explaining these the quartzite rocks, they're always talking about torrential paleo rivers and stuff like this when they talk about it. But the trouble is, where you find them a lot of times is on tops of mountains and places that, and for the ones in Oregon and Washington, they say, well, they came from the Rockies in an ancestral Columbia, Clearwater, or Snake River. You know, even though if you include the bending, you're talking about 600 miles of transport. The trouble is, the ones we found in the Blue Mountains and even in a valley near the Blue Mountains, there's no paleo river that they even come close to putting them in Central Oregon. So, you know, they have answers for these things. They attempt to explain them, but usually their explanations don't hold water. Pardon the pun. Way back in the back. Okay, cavitation. Here's the guy who could talk about that, but here's my summary of cavitation. And you can correct me if I don't get it right. Cavitation works with shallow, fast water, moving at high speeds, but shallow. If you have deep water, it doesn't work. Correct? Yeah. And that's the problem in the flood. I don't think you're going to have a lot of shallow water. I think you're going to have a lot of deep water. So cavitation is not going to be, I don't think, a major player in the flood, except maybe in canyons or something, special local areas you might have cavitation. Yes?
You said that what came off the mountains moved out onto the continental shelves.
Yes, I didn't go into that. Yes, it comes out as a sheet. You remember the sheet flow?
So would you expect to see two depositional features on the continental shelves, one from the original flood and then the secondary one coming off the mountains?
Channelized erosion forming the submarine canyons?
No, two sets of depositional features. The original deposition from the flood, and then it should come down off the mountains and lay on top of that afterwards.
See, as the mountains become exposed, you're getting less and less force to produce the continental shelf. So you're going to get more channelized flow once the mountains are appearing above the water. Did I understand you right?
Well, all that material that washes off has to stop someplace.
I think that's where he said the drawing you showed right there. There's a continental shelf and then what gets deposited.
Yeah, the continental shelf gets deposited first. Okay, here's a graph of the continental shelf. It's a very unique feature. It's over off every continent as kind of like a bathtub ring. But it's a mysterious feature because it's so shallow going out, and then it has a kind of a drop-off, kind of like a delta along the continents as a sheet delta, you could think of it. Some continental shelves are hundreds of miles long, but here's a picture of one from a textbook. One geomorphologist said this is too unusual of a profile. Nature should cause a gradual profile down into the deep sea like that, not one that sticks way out like that into the ocean at a shallow depth and then has a drop-off. That's the continental shelf, and I believe that's the material eroded from the continent as a sheet. Like you were saying, it has to go somewhere, and it has to be deposited somewhere, and where it's deposited is where the currents slow down, and that'll be when it hits deep water. And the deep water will be on the continental margin. And we can show that down in this area below the shelf, there are huge basins. In fact, some of these continental shelves have a huge amount of sedimentary rock in them, like off the east coast of the U.S., the Baltimore Trough, 200,000 square miles, up to 18 kilometers of sediments. Let's see, translated into miles, that's what, 12 miles? 12 miles of sediments. And this takes up the eastern part of the continental shelf and the continental slope. You have a huge hole that goes parallel with the continent. It's called the Baltimore Trough. And this is typical of a lot of continental shelf. You have a huge deep water. So as the material is coming off the continents, it's going to slow. And that's where it's going to drop its load as it's spreading out. And that's why we have such, and even this, that's why we have this going way out here for sometimes hundreds of miles, where it is very shallow. And even by seismic reflection profiling, the sedimentary rocks are very flat, way down in here too.